In this video, we're going to develop a way of finding out the greatest and the smallest values of a function for a given constraint. So this function here is a surface living in 3D space. This constraint here is living in a 2D plane. So it's just your x and y, and you always have to satisfy this, meaning your domain is on this ellipse. So looking at this surface, where's the highest value? Where's the highest and the lowest points on this surface? But the domain has to be on this ellipse. So what that means is this. So if you look down on this surface, it will look like this, and this is our constraint. We have to live on this ellipse. And where is the highest value? Well, the highest value could be here and here. Where are the lowest values? Well, it's going to be somewhere around this region and this region, because if you look at it from this angle, the highest values would be somewhere around here and somewhere around here, and the lowest may probably be somewhere around here and somewhere around here. So we're going to develop a way of locating those points. So looking at this, currently we've been given a function and we've been given this constraint. This constraint is living in a 2D plane, x and y. Currently this function here is of this form. So you input two values and it will spit out the height, the elevation, or this thing, or we can call it z. If you look at this is really in this form here. It's living on a 2D plane. This is living in a 3D plane. So we want to convert this into something of this form, so that we can later work out the gradient vectors of both this function and this function. Well, if let's try and convert this. Currently this thing here is of this form. Let's transform it into this form. So looking at this function here, take away 1, that will then give us this. Now let's just turn this into a function. So now when you plot this into a 3D graphical calculator, it will then give you this surface. Now so now it is of this form here, which is the same as this form here. So you input two values and it will spit out an elevation. So this thing here will then give us this surface. But we want to look at a specific case where it spits out the number 0, because that will have an elevation of 0. So looking at this function, which is this thing here, we want to look at a specific case where it spits out an elevation of 0, which is this thing here. Well, this thing here is this ellipse. So it's really us looking at the same thing. Up here, this was our constraint. It was given to us, but we want to turn it into this form by creating this function. So that function there, we want to look at it in such a way that it will spit out a value of 0. Now this is talking about this ellipse here, and which is the same as this thing here. So hang on, let's start again here. We've been given a function here, we've been given a constraint. Turn this constraint into a function and then look at a specific case where it has an elevation of 0, so which will then give us this. So we are currently hang on, we are currently here. We've got a function, we turned our constraint into this function, but when you look at a specific case of it spitting out an elevation of 0, you're talking about this ellipse. So we always have to look at a case where this spits out a value of 0, because that's our constraint. So just remember that we are living on this ellipse here. That's in effect our domain. We can only live on this ellipse. Now looking at our function, if we look at it when it spits out an elevation of 1, so that will then give us this level curve here, and then this one here, hang on, 1. So when it spits out an elevation of 1, it will give us this line and this line. When it spits out an elevation of 2, that will give us this level curve here, 2 and 2. And then when it spits out 3, that will then give us this level curve here and this level curve here. When it spits out -1, it will then give us this level curve here, -1. And then -2, -3, and so on. So -1 will give us this level curve here and here. And then -2 would be here, -2 would be here, and so on. We want to find well, really the highest point will, well, this has an elevation of 3, this line here. This has an elevation of 1. We don't want the 1, we want the 3, but the thing is, the level curve on 3, we can't reach 3 because we have to live on this domain. So and bear in mind that because this is a smooth surface, in between 2 and 3 there will be millions of level curves. There will be millions of level curves. Well, it turns out that we want this point here, and this point here, and this point here, and this point here. We don't want this point here because it has an elevation of 1. We want the level curve of 3, but we can't reach 3. So so it turns out to be here. But how do we develop a way of locating this this point here? Well, the way we do that is by looking at this, compute the gradient vector. That will then give us this thing here. So and then compute the gradient vector of this. So remember, we've already seen that the gradient vector, when you have a 3D surface, if you blindly compute the gradient vector then lives on a 2D plane. That's why it's just I and J. It lives on a 2D plane, and it's always perpendicular to so if you compute the gradient vector of this, it will then give you this. So what that means is you now have the ability to work out the gradient vector will always be perpendicular to the tangent of wherever you're looking at. So your tangent looks like this, and it's always at 90 degrees to the tangent. If you look at this gradient vector here, the gradient vector here, the tangent looks like this, and it will always be at 90 degrees. So let's say you're looking at this bit here, the tangent looks like this, and it's always at 90 degrees. If you look at the gradient vector here, let's look at this point here, the tangent will be something like this, and it will always be at 90 degrees. So by you computing the gradient vector, you're always able to find something. You're always able to find the vector that's always at 90 degrees to the tangent. Hang on, let me draw some more, and then this thing here. So the gradient vectors allows you to locate all these vectors here, and then if you compute the gradient vector for this function, it will then give you this. What that means is, hang on, you have you have all these vectors here. I don't know if it's pointing this way or this way or this way, but all that I know is that it's going to be tangent. It's going to be 90 degrees to the tangent. So let's say, looking at this gradient vector here, let's look at this point here. Is that 90 degrees to the tangent? So it could be pointing this way or this way. Well, to locate this point here, this point here is they share the same tangent. So looking at the red level curve, the tangent is right there, and then looking at the tangent of the ellipse, it will still be the same tangent. Looking at the gradient vector, it will probably look something like this, and then looking at the gradient vector of this, it may be pointing this direction or this direction. It doesn't really matter. You see, the highest point or the lowest point occurs when the gradient vector differs by a scalar amount. So the gradient vector differs by some sort of scalar amount of g. So it occurs here, and then if you look at here, hang on, if you look at this point here, the the tangent will look something like this. So when you look at the gradient vector for the red lines, it would be something like, it would be maybe in this direction here. Hang on, let me erase this. And then if you look at the gradient vector for the ellipse, it may be pointing in this direction or in this direction. I don't really care, but all I know is that it differs by a scalar amount. It differs by this lambda amount, by this scalar amount. So when you compute the gradient vector for this function, it will then give you this. So let me illustrate it in Desmos. So so when you compute the gradient vector, so you can punch in the gradient vector here. You're going to have to figure this out yourself. I managed to draw a vector. Hang on. You're going to have to figure this out yourself, this bit here. So this is our vector here, our gradient vector. So no matter where you are, it will draw the gradient vector for you, and it's always at 90 degrees to the tangent line. So let's jump to a level curve of 3. So let me zoom out. So a level curve of 3 will look like this. Notice that it's always at 90 degrees to the tangent. So let me zoom back in. So let me jump down here. So now if you move along this level curve of -1, I think, it will look like this. -2, let's jump to a level of -2. It will look like this. Jump to a level of -3. It will look like this. Over here, it will look like this. So build this for yourself and play around with it. So this is, and then jump to level curve of 3. I think this is 3. This is 1 here, and then now let me jump back to here. So when you compute the gradient vector for this function, it will then give you this thing here. Punch that into Desmos. So where is it? It's here. You're going to have to figure this bit out for yourself. So so wait there. So let me think. Where am I? Hang on. How do I drag this? Hang on. Let me think. C and D, which is here. Okay. So if I drag this, see, oops. So notice that the gradient vector is always at 90 degrees to the tangent, and it occurs when it's at this point here. Hang on. And so remember, this blue ellipse, we always have to live on this blue ellipse, and it occurs, the maximum or the lowest occurs when the two are parallel to each other. So so let's look at this over here, and then look at it over here. Notice that they're parallel to each other. If you get it perfectly correct, they're parallel to each other. And then there's another point over here somewhere, and then let me move this over here. See that? They're parallel to each other. They differ by a scalar amount. And then look at this point here. So in the next video, we're going to locate these 4 points. Okay, so so hang on, let me jump back to here. So those 4 points occur when this is satisfied. And also remember that you always have to live on this blue ellipse. We will continue in the next video. Okay.